Hello, ladies and gentlemen. I am Dr. Claudia Albers, Planet X research and professional physicist. And today I'd like to bring to you another one of my articles. This one is entitled Planet X and Gravitational Tuning. Now, figure 1 below shows Planet X system stellar cores in the Sun's corona and in the Earth's atmosphere, drawing material from the Sun and the Earth. The small stellar core on the left is drawing coronal plasma or solar atmosphere, and the one in the center is drawing material which is denser, liquid plasma from the Sun's surface chromosphere through a gravitational vortex. This seems analogous to the water-spout stellar core on the right, which you see here, which is in the Earth's atmosphere and which is drawing liquid water from the Earth's surface. The fact that a vortex forms indicates that the gravitational attraction on the water is very strong, and yet the object does not seem to have much ability to draw atmosphere. This suggests that there is a tuning effect going on. Stellar cores draw material of specific gravitational potential, and since the smaller ones seem to draw only atmosphere in the Sun's corona, it is likely that they are tuned to material which has a comparable gravitational potential to their own gravitational potential. This would mean that stellar cores' gravitational influence is tuned to material with a gravitational potential comparable to their own gravitational potential. So very low gravitational potential stellar cores interacting with Earth are only able to draw atmosphere, and stellar cores of much higher gravitational potential will be able to draw material from the interior of the Earth, such as magma. Magma is the material on Earth which has the highest gravitational potential besides the material in the Earth's core, as gravitational potential increases with depth. And you may look at Article 514 entitled Stellar Cores or Gravitational Poles or Superprotons. And you can see here an illustration of the Earth or another planet which has a core. All celestial objects have a core, which is what generates the object's gravitational field. And then we have, it's a pole. It also generates the positive electric field that the planet has. Now, the gravitational potential of the object it increases as we move towards the center of the celestial object. So it increases with depth. It will decrease with distance from the center of the object. So the atmosphere will have, the material in the atmosphere will have the lowest gravitational potential, and the material in the magma closest to the surface of the object will have the highest gravitational potential. Now, with a star, it's similar, except stars are much larger objects, so all the material would have a much higher gravitational potential than the material that comprises a planet. But also stars have a liquid layer, which we can call the chromosphere, that goes all the way to the surface, and then they have a gaseous atmosphere. So now, the larger the stellar core, the more gravitational potential it is likely to have. The Sun would have a much larger gravitational potential than the Earth, and thus all material making up the Sun would have a much higher gravitational potential than all the material on Earth, including the Earth's core. The magma at the surface of the Earth's core is then likely to have the same gravitational potential as the core. And so this magma would have the same gravitational potential as the core. So then it should not be surprising that a stellar core that has lost all its layers of material but has some gravitational potential energy left inside, and therefore a certain gravitational potential, will draw material that will then become its inner layer of material, which has the same gravitational potential as its core does on its surface. So the Earth's core would have a much higher gravitational potential than all the material that would make it up, but the magma at the surface would have the same as the core. And the Earth's core would then have the appropriate surface gravitational potential with respect to the Sun in order to be at the radial distance from the Sun that it is. And the fact that the Earth is quite far from the Sun shows you that the Sun must have a much, much higher gravitational potential than the Earth has, than even the Earth's core has. A stellar core with comparable gravitational potential to the Earth would thus tend to remain at the same distance from the Sun that the Earth is in. Thus, the largest stellar cores are likely to go to the Sun, and the smaller ones are likely to only be able to draw material from the planets in the solar system. So the planets, therefore, are at the appropriate distance from the center of the Sun, depending on their gravitational potential. And remember, gravitational potential is energy per unit mass. So even though they may have more mass, like Jupiter does, than the rest of the planets, it does not mean that it has a higher gravitational. It has more energy than all the other planets because it has less mass. But the average gravitational energy is less than, for example, Earth's. And Mercury would be the planet that has the highest gravitational potential because it is the innermost planet. So there seems to therefore be a gravitational tuning effect which matches gravitational energies of the gravitational source with the matter it is drawing to itself in the stellar cores. The stellar core which is creating the water spout vortex in figure 1 is likely to therefore have the exact same gravitational potential as water on the surface of the Earth. And the one in the Sun's corona, which also creates a gravitational vortex underneath it, most likely also has the same gravitational potential as the chromosphere on the Sun's surface. Now, the water spout stellar core will still have a gravitational effect on the atmosphere. It will create a low pressure region on the atmosphere, suggesting that it has a weak attractive effect on the material in the atmosphere. But it is not able to attract it to the point that it becomes part of its inner layer. A stellar core tuned to magma would then mainly attract magma and have a very weak attraction for water and atmosphere. It would create an even weaker low pressure and would also create a small bulge on the surface of the ocean, but it would never draw it in a gravitational vortex like the water spout stellar core does. Now here you see one of the largest stellar cores that have come in towards the Sun. It obviously has a gravitational potential which is comparable to the Sun, and the Sun reacted strongly to it, so it's likely to have a gravitational potential which is similar to the Sun's core own gravitational potential because it had such an explosive effect on the Sun. Now, this object turned out to be 7 times the size of the Sun. You may look at Article 321 for how I estimated that. And it is able to draw material from deep within the Sun. Now, this is just the core of what was once a star, and a core seems to be only about 1/5 the size of the objects we know anything about, which is the Earth and the Sun. Well, we don't know that for sure, but we know that the Earth's inner core is about 1/5 of the size of the Earth. So it's likely that stars also have cores that are about 1/5 the size of the whole star. And if that's the case, that means that this object was the core of a star that was once 35 times larger than the Sun. And that would mean that if it now has energy which is comparable to the Sun, that we can calculate what its initial gravitational potential was, and therefore how much of it lost when it died. And to do that, we'll start with the gravitational potential energy from Newton's law of universal gravitation to figure out what is the relationship between gravitational potential and radius. And here's the equation for gravitational potential energy. G is the gravitational constant. M would be the mass of the object we want the gravitational potential for. M would be the mass of an object on its surface, and R is its radius. Then to obtain the gravitational potential, we take gravitational potential energy, divide by mass, we get G M over R. I know there's a factor of minus 1, but it doesn't matter. I just want the relationship. And then the mass would be the density times the volume. Volume of a sphere is 4/3 pi r cubed. And so we have an r cubed there divided by r. It means that we end up with an r squared. And therefore that potential, gravitational potential, is proportional to the radius squared. And here we have used the fact that mass is density times volume. So gravitational potential is proportional to radius squared, and since the stellar core above has a radius 35 times larger than the sun's, if it now has comparable potential to the sun, it must have retained only 1/35 squared, or 1/1225 of its initial gravitational potential when it died. And this is likely to be typical of all the stellar cores. Their gravitational energy has decreased by a factor of about 1,000. So in conclusion, Planet X system stellar cores tune in gravitationally to matter that has a comparable amount of gravitational potential, thus showing that there is a tunable effect to the gravitational interaction. Thus, the larger stellar cores would go to the sun to absorb material, and smaller stellar cores would go to the planets in the solar system. It is likely that the Planet X system stellar cores' gravitational potential after death was about 1,000 times less than when they were alive. And these are the references. This is Dr. Claudia Albers, Planet X physicist. Thank you for watching.